Okay, we're good. Thanks, Sahar. Appreciate that. All right. All right, let me get back to the presentation here. Okay, so we're moving down in terms of decreasing bond strength. Now, one of the things that I think is important for you to understand, especially as we transition to some of the new material today, is that as bond strength decreases, okay, the distance over which those bonds will form also decreases. Okay, so covalent and ionic bonds are some of our strongest types of bonds that form between two molecular species, and the bond distance, the distance over which that bond can form, is fairly long. But as we get into those weaker bonds like van der Waals and hydrogens and hydrophobic interactions, those bonds only form over very short or small bond distances. And this will become, the relevance of this will become very important for drug receptor binding in a few minutes. Okay. Bond energy for electrostatic bonds like ionic bonds are 5 kilocalories per mole. We talked about this the other day. And there are a number of functional groups here that you need to know that can participate in the formation of ionic bonds. Now we're getting into a little bit of medicinal chemistry. Dr. Skabinski is going to dig very deeply into this subject at the end of the module, but I needed to introduce some of these basic concepts to you so you can understand what we're talking about, okay? Hydrogen bonds are the next. Their bond energy ranges from 2 to 5 kilocalories per mole, and they typically form between the highly positive charge of a hydrogen ion and the negatively charged atoms like nitrogen, oxygen, and sulfur. Okay. And what we often see in terms of drug receptor interactions is the formation of multiple hydrogen bonds between drug molecules and receptors. And the more hydrogen bonds that form, the more stable the drug receptor interaction is. So even though the bond strength, the bond energy is very low with these types of bonds, if you form multiple, right, bonds, it can lead to a fairly strong interaction between the two species. Okay, it's sort of like if you were to try to pick up a car with a piece of twine or string, right? That's ridiculous. It could never happen. The twine would break. It's not strong enough. But can you imagine? And again, this is just a kind of a far-fetched analogy. Can you imagine using 100,000 pieces of twine to try to pick up a car? Okay. In that case, you might be able to do it. Okay, so again, with small bonds added together can lead to strong interactions. Okay. Now, one of the things about hydrogen bonds is that they play an important role in establishing the selectivity and specificity of drug receptor interactions. We're going to talk about selectivity and specificity today in more detail. Okay, and it's often a concept that students can get a little bit confused about. But, you know, I think that the thing to understand about that right now is that selectivity and specificity, i.e. the ability of a drug molecule to be able to identify a specific receptor and bind only to that receptor, okay, amongst a whole group of receptors, is very desirable for a drug, right? We want our drug molecules to be as selective in terms of the receptors that they bind to and specific as possible. Because when you have a drug molecule that is promiscuous, as we said before, and that's a pharmacological term that we use, meaning that a drug or a chemical compound will bind to lots of different types of unrelated receptors, what we end up getting is side effects. Okay, and that is one of the major reasons, not the only, but one of the major reasons that we have side effects with drugs is because they lack the selectivity and specificity necessary to avoid some of those side effects, i.e. they will activate or block receptors that we don't want them to. Okay, everybody got that? All right, so van der Waals interactions, and I think Eric, this was your question. It's taken a while to get here, but we're here now. Okay, so these are some of our weakest chemical bonds that form between drug receptor molecules, and in order for these bonds to form, okay, the drug molecule and receptor molecule has to be very, very close together. So you can imagine as a drug molecule is coming in towards a receptor, okay, And let's say this is the receptor binding pocket here, my hand that's squeezing, and this is the drug molecule here. In order for the van der Waals interactions to occur, these two species have to get very close together, which requires a tight fit between the drug molecule and the receptor binding pocket. So there has to be a precise and tight fit. Okay, sort of like if you live in an apartment or a dorm room, right, and you have a keychain, and if you're like me, you might have a bunch of different keys on your keychain, right? And maybe if you're new to that dorm room, you're not really sure you remember what the key are. You might try a couple of keys in the door lock just to try to get the door open. One key will fit really well. It's got a very precise fit and will turn the tumblers in the lock and open up the door. Other keys won't even fit into the keyhole. And so this kind of lock and key analogy was used and is still used to describe some of the very basic characteristics of drug receptor interactions. Okay, so to extend this analogy to van der Waals interactions, in order for, let's say, a van der Waals interaction to occur between the key and the lock, that the key has to be able to fit through the keyhole and interact with those tumblers inside the lock, which will allow it to open up. That would be an example of a real tight fit and close interaction that would facilitate van der Waals interactions. Now, one of the most common molecular or atomic structures that we see that participate in van der Waals interactions are aromatic rings. Okay, so if you're looking at a drug molecule and it's got an aromatic ring or multiple aromatic rings, that doesn't guarantee that it's going to form van der Waals interactions, but it's a possibility for sure, and it's a very common type of thing. Okay. This type of bond plays a significant part in determining drug receptor specificity, okay, or fit, precise fit. So right now, I think the way to understand the difference between selectivity and specificity is that selectivity is the ability of a drug molecule to recognize a particular receptor that it's going to bind to in a group of unrelated receptors. Right. So it's sort of like if you have a, let's say a sister or brother, and you walk into a crowded room, okay, you're able to, after scanning the room a little bit, to find that person, right? And maybe that's the person that you want to talk to, and you go over to talk to them. That's selectivity. You're not going to mistake somebody else for your brother or sister. Okay. Now, specificity occurs kind of after that. All right, where the drug molecule fits into the receptor molecule. All right. So again, just because a drug molecule wants to bind to a receptor doesn't mean it has the appropriate atomic shape, size, shape of functionality to allow it to bind to that receptor molecule because of the need for a precise fit. And we're going to talk all about that in a bit. So the bottom line with van der Waals interactions is that they're important for drug receptor specificity. And the reason for that is because in order for these bonds to form, the drug molecule and the receptor molecule have to come incredibly close together. Okay, and I have a kind of a cartoon picture coming up that might explain this a little bit better. Okay, Eric, did that answer your question?
Yes, it did. Thank you.
Okay, great. And then hydrophobic interactions, again, these are nonpolar compounds. The association between two nonpolar compounds, you can see those here represented by the black ovals. Okay, when the interaction occurs, it excludes polar solvents like water. Okay, and they're not very specific types of interactions, but they are important in drug receptor interactions.
Dr. Coy.
Yep.
I have a quick question. So it seems like most of the interactions have like a way you can tell that it's capable. Like you said, the aromatic rings are looking at the functional groups for some of them. But for covalent bonds, would we have to sort of know that it's capable because it's okay.
Yeah, absolutely. It's it's not as easy to predict whether a covalent bond is going to form between a drug molecule and a receptor molecule. You're absolutely right. I won't ask you to do that. Okay. Now, what I will ask you to be able to do is to, if I give you a drug molecule, like I did in the memoranda 1, right? I gave you a drug molecule and asked you to look at the functional groups and predict. Just say, hey, what are some possibilities here based upon these functional groups? It doesn't mean they're going to form. All right. If I give you a drug molecule and a receptor molecule with functional groups, okay, can you predict what types of bonds might form between the two of those? Okay, and it's just really about understanding and knowing what the functional groups is, and then knowing how to pair those up. Okay, make sense? Good. All right, so I think we ended here yesterday. We were talking about drug receptor biophase and the dynamics of drug receptor binding. So let me define what the biophase is. So the biophase is essentially an area of solution or fluid that surrounds the receptor binding pocket. Okay, so if you think about a protein receptor, let's say a membrane receptor that sticks out of the surface of a cell membrane and into the extracellular fluid, that protein receptor is surrounded by that extracellular fluid, right? Okay, and the extracellular fluid that is right around the receptor is typically referred to as the receptor biophase, and this is where drug receptor interactions occur. Okay. So when you expose, or when a cell is exposed to a hormone or neurotransmitter or a drug molecule, that drug molecule will enter into the extracellular fluid surrounding the cell, at least we believe, right? And the drug molecules will then begin to move around the cell surface and the receptors via Brownian motion. So there's a random kind of motion of drug molecules in the receptor biophase, and that's fueled by Brownian motion. If you took physical chemistry in undergraduate, you'll know that all atoms and molecules have inherent vibrational, rotational, and translational energy to them that allow them in solution to move about randomly. They're not just static floating molecules, but they do move around randomly, okay? And so we think that this random movement of molecules around the receptor and the number of molecules that surround the receptor will facilitate a drug molecule coming within close proximity of a receptor or bumping into a receptor. And at that point, those bonds that we talked about can begin to form, okay? Drug molecules are initially attracted to receptors that they're going to bind to via ionic bonds or ionic forces, okay? So we're going to exclude covalent bonding for a second here. Okay, we're not going to talk about that. We're just going to talk about reversible bonds that form between drugs and receptors, because this is normally what happens physiologically. Okay. So, anytime a ligand or drug molecule or hormone, neurotransmitter, whatever we're talking about, okay, it's floating around the receptor biophase, and if it gets close enough to the receptor, it will begin to be attracted to the receptor binding pocket via ionic forces. And as that drug molecule is pulled into the receptor binding pocket, okay, some of those other bonds form that we were talking about, like hydrogen and van der Waals interactions. And hydrogen and van der Waals interactions allow the drug molecule to rotate and move so that it can bind with a precise, tight fit onto the receptor, okay? And then as the closer it gets, you get closer interactions, and then you can get van der Waals interactions that occur, okay? So the bonds will form, depending on their bond strength and the bond distance that they form over, in kind of a sequence. Ionic bonds typically occur first. As the receptor is pulled into the receptor binding pocket, hydrogen bonds begin to form, and then we have finally van der Waals interactions that help to orient the ligand molecule in the receptor binding pocket so that it can bind tightly and with a precise fit. Okay, and when those bonds form between a drug molecule and a receptor molecule, okay, they're reversible. So there's constantly an association, dissociation between drug molecules and receptors. Okay, it just doesn't bind and stay bound. Okay, drug molecule will bind, or a hormone or neurotransmitter will bind, and it will unbind, provided that it's forming ionic hydrogen and van der Waals interactions and not covalent interactions. Okay. And then we have a cartoon picture here, kind of an animation that I put together years ago to kind of explain this. So you can see here, we've got all of our drug molecules moving around in the receptor biophase in a random pattern due to Brownian motion, right? And initially, the bonds that will form between a ligand molecule and a receptor are your ionic bonds, right? So you see this red one here is beginning to be attracted to the receptor via the formation of ionic bonds. And then as it's pulled into the receptor binding pocket, we have the formation of hydrogen and van der Waals interactions over here, okay? Now, this isn't a perfect example because we don't necessarily see that round circle, kind of moving and orienting itself so that it can fit tightly into the receptor binding pocket, but that's occurred, okay? Everybody understand that concept? Any questions?
Dr. Kohei.
Yeah, Justin.
Good morning. So
Good
I
morning.
was wondering, do all drug receptor interactions involve all of these? Do they always need ionic, hydrogen, and van der Waals, or?
Yeah, that's a great question, Justin. And the answer to that question is no.
Okay.
That's not always the case. Typically what you're going to see, typically you'll see at least more than one of these types of bonds that form, okay, between these types of species. So, as a scientist, I am reticent to use the terms always and never,
Yes.
right? Okay. But I think, it's kind of a general, the way I'm presenting it here is just to give you a general understanding of how these types of interactions, or how we think these types of interactions actually occur, okay? Clearly some of these bonds have to form in order for a ligand to bind to and activate a receptor, right? But is it a requirement that all three of these types form? No, it is not, okay? Any other questions? Okay, so here's actually a real example of the types of chemical interactions that occur between a real ligand, okay, and a real receptor. Now, remember, in order for a ligand molecule and a receptor molecule to form chemical bonds, they both have to have compatible functional groups, right, that will participate in ionic, hydrogen, or van der Waals interactions. And in this particular case, I have an example of a ligand that's binding to a receptor using all three types of those bonds, okay? The receptor here that we're showing is a beta-2 receptor, which is an adrenergic receptor. It's a G protein coupled receptor, right? A 7-transmembrane spanning G protein coupled receptor. And the viewpoint, or our vantage point, is we're looking at the receptor from the top. We're floating on top of the receptor here, and we're looking down on the receptor. So you can see here are the 7 transmembrane spanning regions. That's what the TM stands for, transmembrane, okay? And they're all numbered 1 through 7, okay? And you can see how these transmembrane regions form a binding pocket, okay? Now, on each one of these transmembrane regions, okay, or on some of them, and I think the ones I'm going to talk about are transmembrane region 3, 4, 5, and 6. What do you see sticking out of these circles?
Functional groups.
Functional groups, right? And those functional groups are actually, each one of those functional groups is actually a part of a specific amino acid residue in that protein, okay? So for example, in transmembrane region 3 here, we see a carboxyl group sticking off of it, right? Where does that carboxyl group come from? It's a part of aspartic acid. And that aspartic acid is at position 106 in the protein, okay? This aromatic ring here, right? Where does that come from? Well, it's a part of an amino acid residue in transmembrane region 4, which would be, anybody know? What does F stand for? Dr. Skabinski didn't make you do your single letter? No? Phenylalanine? Okay. And then we have serine over here. Okay. So again, and I won't ask you to know single amino acid abbreviations. You don't need to be able to recognize those. This is just an example here. Now, if you take a look here, in green here, we have our drug molecule. And this should look familiar because you've studied these before. This is a catecholamine, okay? A substance that's actually released by the adrenal gland. Anybody want to hazard a guess what this is? Got the catechol ring here, right? Theta and alpha carbon. Anybody?
Is it epinephrine?
It's epinephrine. Absolutely. Very good. Okay, so what we're showing you here are the chemical bonds that form between epinephrine and a beta-2 receptor. And look at all of these. So the amino group here, the terminal amine in epinephrine, forms an ionic interaction with a negatively charged carboxyl group on transmembrane region 3, right? Over here, the catechol ring, okay, forms a van der Waals interaction between the phenylalanine at position 163 here in TM4 and phenylalanine in transmembrane 6 at position 288. So we have two van der Waals interactions going on. So the green catechol ring is actually sandwiched between the two phenylalanines. And then we have two hydrogen bonds that form between the hydroxyl groups on the catechol ring and the hydroxyl groups here on serine at position 188 and 192. You don't need to memorize this. You don't need to, this is just an FYI example, okay? So if I were to give you a picture like this on the exam, okay, and say, can you determine what types of bonds are likely to form, okay? I would expect you to be able to say, oh, look at this. This amino group here is close to this carboxyl group. We'll probably have an ionic interaction here. Or these two aromatic rings are close together. Probably have a van der Waals interactions going on here. Or we have two hydroxyl groups that are close together, hydrogen bond interactions, okay? Got it? Any questions about that? So this is just kind of to illustrate an actual example, and I would expect you to be able to, label the different bonds that would form between these types of functional groups, okay? Make sense? And all you need to know is the types of functional groups that form with those chemical bonds. That's all you need to know. Okay. All right. So let's talk about some other some general characteristics of drug receptor binding or drug receptor interaction. So things that we can use to characterize the nature of the interaction between a ligand molecule and a receptor. One of the things I'm going to tell you guys right up front here, and I've been doing it for the last 35 minutes or 30 minutes or so, is the term that I really want to use, I think is most correct at this stage of the game, is ligand. I'm using drug, neurotransmitter, and hormone, right? I'm kind of using all these terms interchangeably, and I'll try to be more deliberate and say ligand. And a ligand simply is any molecule that will bind to a receptor. So that's a big, broad term that encompasses things like drugs, neurotransmitters, hormones, those sorts of things, okay? So the first thing we're going to talk about is binding affinity, all right, or KD. Now, this is a term you guys learned about in biochemistry when you learned about enzyme-substrate interactions. And Dr. Skabinski may have even talked about it in context of drug or ligand receptor interactions, okay? Binding affinity is a measurement of how readily a molecule will bind to a receptor, all right? So it's a reflection of the strength, okay, of the interaction between a drug molecule and a receptor molecule. So that's a verbal definition that I think is important for you to know, okay? Being able to describe that in your own words. Now, we have a mathematical definition and experimental definitions that we use because we can actually measure binding affinity under laboratory conditions, okay, to see how well or how readily a ligand molecule will bind to a receptor, okay? And the kind of the laboratory experimental definition of KD is a little bit different, okay? It's defined, and when we measure KD, as the concentration of drug required to bind 1/2 of the receptors in a fixed receptor population. So when in order to really fully understand this, you have to understand how we measure binding affinity in the laboratory, okay? And very simply, when we do this, and it's this is an oversimplification, okay, of binding assays, but essentially what we do is we will take our receptor that we want to, and our drug molecule that we want to measure the interaction with, and we begin to expose the receptors to small doses of our ligand and measure how many receptors the ligand interacts with. And we keep bumping up the dose of our ligand and continually measuring how many more receptors are bound until we get to that 50% mark, okay? And that is the reference point that we all agree to use as the binding affinity, all right? And we're going to explore KD an awful lot and what that means. But for right now, we have a verbal definition, and then we have kind of our experimental or laboratory definition, which is the concentration of drug required to bind 1/2 the receptors in a fixed population, okay? The better the binding affinity, all right, the less drug you need to bind 1/2 of the available receptors, okay? Now, from a numeric range standpoint, for most drug molecules or ligands we're going to be talking about, good binding affinity is anywhere between 1 and 100 nanomolar, okay? That is the value, that's the concentration of drug required to bind 1/2 of the receptors is 1 to 100 nanomolars. That's usually a pretty good range. Anything above 100 nanomolar, we tend to start to get into, less and less binding affinity. And then, things below 1 nanomolar, well, that you're getting a very, very high degree of binding affinity there. And I'm using a metric term here, nanomolar. Okay, there are three different metric units that I think you need to be familiar with for this exam, okay, and for what we're doing. You need to be familiar with picomolar, which is 10 to the minus 12, okay? Which is probably a metric term that you're not familiar with because it's so tiny. Picomolar, 10 to the minus 12. Nanomolar is 10 to the minus 9th, okay? And micromolar is 10 to the minus 6th. All right, those are 3 metric units that you need to be familiar with if you're going to navigate binding affinity with me over the next week or so, okay? Picomolar, 10 to the minus 12th. Nanomolar, 10 to the minus 9th. Micromolar, 10 to the minus 6th, okay? And as a general rule of thumb that works 99% of the time, the higher the KD value, the greater the KD value or the higher the KD value, the lower its affinity for the receptor, okay? So if I have a drug molecule who has a KD value for its receptor of 1 millimolar, right, which is 10 to the minus 3, very, 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 very low binding affinity, okay? If I have a drug molecule and a receptor molecule whose KD value is 10 to the minus 12th, 1 times 10 to the minus 12th, or 1 picomolar, that's very high binding affinity, very strong binding affinity, okay? So there's an inverse relationship, okay, between the numeric value for KD and how strong a drug molecule or ligand molecule will bind to a receptor, okay? And I'm going to give you specific examples of this. We're going to work with some numbers over, you're going to have plenty of practice with this. You're going to be wizards at binding affinity by the time we're done, okay? Now, binding of a drug molecule to a receptor can be reversible or irreversible. We just talked about that, right? And what determines this? Well, simply the types of chemical bonds that form, right? If we have our electrostatic bonds, right, like ionic hydrogen van der Waals interactions, then the binding is typically reversible. If we have the formation of a covalent bond between the drug molecule or ligand molecule and the receptor, the binding is typically irreversible, okay? Because covalent bonds typically cannot be broken under physiologic conditions, okay? Binding of the drug to the receptor is a stereoselective reaction, okay? And you'll remember this from last week when we talked about stereoselectivity as one of the characteristics of a ligand molecule or drug molecule, all right? If you have a drug that's produced as a racemic mixture, so you have two optical isomers in the formulation, only one of those optical isomers is going to bind to its target receptor. The other one won't, okay? Because of the orientation of the functional groups on that drug molecule. Okay. And number three, and this is very, very important, I've already iterated this, the specificity of drug receptor binding is never absolute, okay? I don't know of one type of ligand or drug or neurotransmitter or hormone that binds only to one receptor at any concentration, okay? So I don't know of any examples of that. All drugs, okay, can bind to multiple receptors. Now, we're going to talk about how we can make a drug receptor interaction more specific and selective, all right, by using the lowest dose possible of the drug, okay? But as we tend to give our patients higher and higher amounts of drug, the probability that that drug is going to spill over and bind to other receptors that it's not supposed to increases. And that increases the probability of side effects, okay? So specificity of drug receptor binding is not absolute, meaning that most ligands, if presented with the right conditions, will bind to multiple types of receptors, okay? And one of those conditions is the amount of ligand that's present in the biological system, okay? The more ligand that's present in the system, the more likely that ligand is to bind to receptors that it's not supposed to. Okay. Any questions about that? Anybody? Okay. All right. So let's do a little quick stop exercise here, okay? So this is, we're gonna do a little work from home here. In fact, actually what I'm gonna do is I'm going to, you guys have this up on your computers? Are you following along on with that? Okay, because what I wanna do is I wanna put you into breakout rooms and let you work on this for a few minutes and then we'll take a break. Let me read through the exercise here. Considering the following scenario, we are running a laboratory experiment to compare the binding affinity of two drugs, drug A and B, okay? We take each drug, okay, and apply each in the same concentration to two identical pieces of tissue. All right, so here we have drug A here, over here on the left. We are applying drug A at a concentration of 100 nanomolar to this piece of tissue that has 10 receptors on it, of receptor X, okay? Then we're doing drug B, and we're applying drug B, which is a totally different drug, at the same concentration, 100 nanomolar, to the same tissue and receptors, and we see that we get three, okay, drug receptor interactions that occur here. Over here we have 5, okay? So what I want you to do, okay, is to tell me, okay, which drug has the greatest binding affinity, okay? And can you tell me something about the KD value, okay, of our drugs, okay? So I'm going to just put you in breakout rooms automatically, okay? And we will, you guys can work on that. We'll come back, and then after that, we'll take a break. Okay? See you guys in a minute. And I'm going to give you only a couple of minutes to do this. So remember, I'm looking at, can you tell me which drug is has greater affinity for receptor X? And can you tell me something about the KD value of either of these drugs? Okay? Go ahead and join your breakout room. Belen? Oh, Daphne? You guys here? Hey,
Professor
Daphne.
Culhane,
Yeah.
I'm sorry, my internet keeps on going in and out, and it keeps on kicking me out of the Zoom meeting. So I
Oh,
missed what
Daphne.
you want me to do. Should I
Yeah,
just
you
go
know,
to?
you know what? Did you get your meeting invitation? Actually, so if you got kicked out, we're actually on, looks like slide 60. And we're doing a little bit of an active learning exercise.
Like you broke up just now. So I got up to the slide. I took a picture of the slide. It just didn't send me to the breakout room because
Oh, okay. So
it
you know
kicked me
what,
out of the Zoom meeting.
Daphne, all I'm looking for, if you're looking at slide 60, just can you can work by yourself, because I'm going to bring people back in a minute or two. Can you tell me which drug A or drug B? Can you hear me?
Yeah, I can hear you now.
Okay. Can you tell me which drug binds more with greater affinity to receptor X, drug A or drug B? And then tell me something about the binding affinity of either one of those.
Okay, I'm sorry. Bear with me because it keeps on having you break up. So I'm
Nope.
catching like every other word of your sentence.
Yeah. So, okay. Can you tell me, it looks like you're frozen now.
And you're frozen.
Yeah. Okay. We're back again. Yeah. If you can tell me what drug molecule binds with greater affinity, okay, to receptor X, drug A or drug B,
Okay.
based upon that
Because it
cartoon.
has more.
Yeah. Right. And can you tell me something
based
about
off that cartoon.
Yeah. Can you tell me something about the KD value?
It must be low. If the KD value has to be low for the affinity to be so high for drug A.
Right. And think about the definition of KD too. It's
You heard me?
Yep.
Okay, good.
Yep. Excellent. All right. I'm going to bring everybody back here.
Okay.
Yep.
Oh, yay. Thanks.
We'll wait for everybody to come back here. We can still have some folks in breakout rooms. Okay, looks like everybody is back. Okay, so let me ask a question here. So we have two drugs here, and we're trying to measure how well each of these two drugs bind to the same receptor. Okay, we apply each of the drugs to the receptors at the same concentration, and we can see here when drug A is applied at 100 nanomolar, we get the formation of 1, 2, 3, 4, 5 ligand receptor complexes, right, out of 10. And over here, when drug B is added at the same concentration, we only get the formation of 3 ligand receptor interactions, or ligand receptor complexes out of 10. So which drug binds with higher affinity to our receptors, drug A or drug B?
Our group said drug A.
Drug
Drug
A.
A, right? Okay. Drug A does, because at 100 nanomolar, it forms 5 ligand receptor complexes, whereas drug B only forms 3. Now, Can you tell me something about the KD value of drug A? Can you tell me what it might be?
Lower than drug B?
It's definitely lower than drug B, absolutely. Can you tell me what the numeric value or the actual numeric KD value for drug A is?
Is it 2.5?
Pardon me?
Is it 2.5?
It's not 2.5.
Will it be less than 1?
Nope, it's not less than 1. Think about the definition. The KD value is the concentration of drug required to bind 1/2 of the receptors in a fixed receptor population.
Is it 100?
It's
now?
100 nanomolar, right? Absolutely, right? Because here we have a fixed receptor population. We only have 10 receptors. And at 100 nanomolar, drug A binds to 5 of those receptors. So it just happens to be that 100 nanomolars in this case is the KD value for drug A, okay? What can we say about the KD value for drug B? Can you give me a specific value for that? There's no way to do that. But what can you say about the KD value? We know it's not equal to 100 nanomolar, right?
It'll be higher then.
It's higher, right? So if, let's say we were to bump the dose of drug B up to 300 or 400 nanomolar, maybe 500 nanomolar, that might be enough to get us to the formation of maybe 4 receptor ligand complexes, or maybe 5 ligand receptor complexes. We just don't know. We have to run the experiment and see. But this is just a very basic experiment example to show you the relationship, to tell you a little bit about binding affinity and how drug receptor molecules or ligand receptor molecules interact with one another. Okay, I think it's time for a break.
Dr. Cohane?
Anybody have any questions before we go on break?
Yeah, I do. I have a question.
Go ahead.
I got lost on how you got the numeric value for KD for drug A.
For drug A. Okay, so it's just based upon the definition. Okay, so if you guys remember, the definition of our KD, if we go back to this previous slide, let me go back one slide if I can. Okay, right here, number 2, KD is also the concentration of drug required to bind 1/2 of the receptors in a fixed population, right? That's one of the definitions. So if we go over here to this example, do we have a fixed receptor population here, meaning that the number is not changing?
Yes.
We do, right? We have 10 receptors. How many receptors are bound up with ligand here in this example?
5.
5, right? So 1/2 of the receptors are bound up with our ligand when we add drug A at a concentration of 100 nanomolar. Okay?
Okay.
And so again, just serendipitously, we picked a concentration here of drug A that binds 1/2 of the receptors so that we can say, okay, this is the KD value. This is the concentration of drug, 100 nanomolars, that's required to bind 1/2 of the receptors. If we were to bump the dose of drug A up to 1,000 nanomolar, Eric, what do you think might happen with our ligand receptor complexes? If you had to make a prediction, if we increase the dose of drug A by 10-fold up to 1,000 nanomolar, what do you think? Would we have more ligand receptor complexes that are formed or less?
Will it be less?
It would actually be more. Okay. Why don't you stick around for a minute and we can discuss that. And if any of you, if anybody else has questions about this, please stick around. Okay. And I can address that. Okay. The rest of you, break time. Why don't we come back in about 7 or 8 minutes? I'll give you the 2-minute warning. Okay.
Quick question, Dr. Cohane.
Yes.
If we had more ligands bound than just half, we wouldn't be able to tell the concentration, right?
We wouldn't be able to tell you what the KD was, right?
Okay.
So let's say our concentration of drug A was 700 nanomolar, okay? And we had 8 ligand receptor complexes that were formed, okay? We know that we're above the KD value, right? But we couldn't target in what that is specifically.
Okay. Thank you.
All right. So Eric, I think that one of the things to remember about, drug receptor interactions, right, is that the more drug molecules or ligand molecules that you have in the receptor biophase, the greater the probability that those ligand molecules are going to bind to your receptors, right? Okay. So if I have a gazillion molecules of drug A in this biophase, right? The probability that one of those molecules is going to come into close enough proximity to our receptor to bind to it is pretty high. Okay. And so in this case, with drug A, we've got enough molecules of drug A in the receptor biophase that half of the receptors are bound up. Okay. If we bump that dose up to 1,000 nanomolar, okay, what do you think is going to happen?
So more like ligand will bind to the receptors.
Exactly. You might have 8 or 9 ligand receptor complexes that are formed. You might bind all of them. You might saturate all of them. Okay. If I drop that dose down to 1 nanomolar of drug A, what do you think might happen?
Will it be the opposite, less ligand?
Yeah, it'll be less than 5. Now we don't know what that's going to be. We can make a prediction. Maybe it's 1 or 2, right?
Okay.
That's all we're doing right now is kind of making predictions.
Oh, okay.
That's it. We're not doing, there's a mathematical calculations and ways that we can specifically determine what the KD value is. All right. But we're not going to get into that because you guys don't need to know it. Okay. All I'm trying to illustrate here is that binding affinity is a reflection of how readily a ligand and a molecule will bind together. Okay. At a particular concentration. Okay.
Sorry, doctor, may I ask you something, please?
Sure, absolutely.
Sorry if I bother asking again about, so the numeric, the number or value is 0.5 because I have 5, I have like 10 receptor and 5 the element that we have bound with them. So I didn't understand exactly which number is the value of KD.
Right. Remember, you have to go back to the verbal definition. Okay. The verbal definition is the KD value is expressed as the numeric value is the same thing as the concentration of drug needed for the ligand to bind to 1/2 of the receptors in your receptor population. Okay. So KD value is always a concentration. Okay. So units of KD value is always expressed in units of concentration, nanomolar, micromolar, picomolar, millimolar, okay? And it's that concentration of drug that it gives you enough drug in the receptor biophase so that half of the receptors down here are being bound up. You're absolutely right, Ali. When you say the 0.5 value here, 0.5 is a representation of the fraction of receptors that are bound up with ligand, right? It's half. But that's not the KD value. The KD value is the concentration of drug, i.e. 100 nanomolar in this case, that is needed for the drug to bind to 1/2 of the receptors in our receptor population. We just picked that number 1/2 as a common value that we can use to compare one drug from another. Okay, that has no special meaning. We could have picked, scientists could have, agreed upon that the KD value is the concentration of drug required to bind 80% of the receptors in a fixed receptor population, or 20%. They just picked 50% as a reference point for everyone to look at. Does that make sense?
Thank you, doctor. Thank you. Yes.
You're more than welcome.
Dr. Gohane, I had a question about this.
Justin, go ahead.
So, although we won't have to know this, but I'm just curious, how can they measure that half the receptors are actually bound to ligands?
Yeah, exactly. So basically what we'll do is we will take, when we do receptor binding assays, Justin, okay, we will take a, cell culture or a piece of tissue, okay, that we want, that expresses the receptor that we're studying, okay? Then we take a radio labeled, well, this is what we used to do when I was a graduate student. I don't think they use radioactivity for this much anymore, but we take a radio labeled ligand, something that's got a like tritium attached to it or a radioisotope of phosphorus, and we
Yes.
apply it to the tissue in a massive amount. Okay, so that it binds to everything. Okay, and then we run our assay where we start to add our ligand, right, that we're trying to measure the affinity of. And
Yes.
we start with small doses, and then we measure how much radioactivity is left in that sample.
Okay. So it's kind of like chase experiment.
Exactly. And so as we bump up the concentration of the ligand that we're measuring, the radioactivity in the sample will decrease because we're displacing those radio labeled ligands.
And then you just measure the radioactive activity. And once it's half, you say, okay, half of them. Okay, that makes sense.
Yeah. So I think these days they use, fluorescence tagged or immunotagged types of ligands. Is a little bit different. But when I used to do this, it was with radioactive isotopes.
More exciting when you used to do it.
well, yeah, just more of a pain, and you know what, right? Because you're dealing with radioactivity.
Yeah, that's true.
Yeah, so it's you have to be a little bit more, obviously a lot more careful, and there's a lot of regulations around storage and disposal, and you had to go through training, and the instrumentation that was needed to measure the radioactive signature in our samples was very expensive.
I can imagine. So when we're dealing with drugs in real life, what would be the optimal KD that we're looking for? Because we don't want it to be too, like you said, you don't want it to be too high of affinity, right? Or do you want it at really high affinity?
The higher the better, actually, because what that will do is that indicates that your drug that you have, all right, is very selective and specific for the receptor that you want it to target. Most of the drugs we're going to talk about in pharmacotherapeutics, a big chunk of them are receptor blockers or antagonists, right?
Yes.
And so, when drug companies are developing, let's say, a new drug antagonist for a receptor, one of the things that they want to maximize as much as possible is that affinity value. Okay, they want that
that makes sense.
as high as possible so that the drug's not blocking other receptors that we don't want it to.
Okay. So it's also affinity for specific receptors, not just overall.
Exactly. We're talking about affinity for a specific receptor.
Okay.
All right. Cool. Anything else? All right, this is the 2-minute warning. 2-minute warning. All right. As we're coming back here, break, anybody have any questions about what we just did in our quick stop exercise there? Okay. Just to kind of recap, we've been talking about the characteristics of drug receptor interactions, right? We've talked about the type of chemical bonds that can form between ligands and receptors, or drug molecules and receptors. I continue to use those terms interchangeably, okay? And we also talked about the characteristics of that binding. So how strong the chemical interaction is, or how readily those chemical interactions will form, is a reflection of the binding affinity, the affinity that the drug has for the receptor, okay? How readily it will bind to it. And again, affinity has a couple of different definitions. It's it's a reflection of how, again, readily a ligand will bind to a receptor, or the strength of the interaction between a ligand and a receptor. Another definition of affinity that is important for us experimentally is that it is the concentration of drug required to bind to 1/2 of a specific type of receptor in a fixed receptor population, okay? And typically affinity values, when we measure them in the laboratory, we consider good affinity to be somewhere between 1 and 100 nanomolar, okay? Micromolar is not great, millimolar is horrendous, okay? And picomolar, 10 to the minus 12th, a KD value in the picomolar range would be tremendously high. It would be a really good, really good affinity between a drug molecule and a receptor molecule. So why do we care about all of this? Unless you're a scientist measuring drug receptor interactions, why do you care as a pharmacist? This is really important because the drugs that you're using, okay, you want to make sure, and you don't have to make sure of this, but the drug companies that develop and manufacture and sell them have, that those drugs are has high affinity for their target receptor as possible, okay? Now, despite that, there's no drug, there's no hormone or neurotransmitter that I can think of that under any condition only binds to one type of receptor, okay? There are circumstances, okay, where the drug molecule might bind to other receptors if it's present in, for example, if it's present in very high concentrations in the body, okay? It might bind to other types of receptors, okay? So when we start patients on drugs, right, okay, one of the reasons we start patients on very low doses of drugs first, right, is to see how they're going to respond, but it also keeps the interaction of that drug with its target receptor very selective and specific, okay? And let's say the patient doesn't respond to that low dose that you start them on. Well, then you've got to increase the dose. And as you increase the dose of any drug that you're giving a patient, the probability or possibility that that drug may interact with receptors that you don't want it to starts to increase. Okay. If you have a patient on a maximum dose of a drug, okay, there might be a high degree of possibility that they're going to experience side effects. Why? Mostly the most common reason for that is because at that extremely high dose, that drug molecule is what we refer to as spilling over and interacting with receptors and proteins that it's not supposed to. Okay, does that make sense? That's the translation from from the bench to the bedside there. Okay.
Dr. Kulhen, that's because the drug can be more in the bio phase.
Yes.
So are going to interact more.
Exactly. So the more drug that you give a patient, right, the more drug that ends up eventually in the receptor biophase, right? And in the receptor biophase, the fluid surrounding, the cell membrane where the receptors are, okay, there's going to be cells make lots of different types of receptors in order to respond to different chemical signals, right? So there's, anytime you administer a drug, there's a possibility that it could bind to your target receptor that you want it to, but it could also bind to other receptors that are present on cells, okay? Now, what is the variable that will determine whether that happens or not? Typically, it's drug concentration, okay? At low drug concentrations, that drug is less likely to bind to receptors that it's not supposed to. But at very high drug concentrations, now the probability or possibility that that drug is going to bind to receptors that it's not supposed to increases significantly. Okay, does that help, Roberto?
Yes.
Okay, great. And that, again, that has a lot to do with the amount of receptor in the receptor biophase and the affinity that that receptor has for its target receptor, as well as the affinity that it might have for receptors that it's not supposed to interact with. Okay? Okay, everybody understand that? So, another way to, again, to humanize and make an analogy of this, okay? Let's say that you have an exclusive relationship with a significant other, right? An exclusive relationship with a significant other, right? So that you are only supposed to be interacting with that significant other, okay? Does that make sense? Now, are there circumstances, right, that could occur that may lead you to develop affinity for and interact with receptors that you're not supposed to, if you catch my drift here, right? Okay. So, so this is the human condition, right? Okay. And so again, what are those conditions? Okay. Well, maybe you're invited to an event without your significant other, and there are lots of attractive people at the event that you're attracted to, okay? Might that increase the probability that you are going to be promiscuous, using that pharmacological term, right? Okay, that's possible. All right, we hope not, but it's possible, okay? To extend that analogy further, right? If you throw in some adult beverages there, right? Okay. That could also, just like increasing drug concentration. So again, I'm trying to, you were laughing and I hope we all take this in jest, but it's a way of really understanding, okay, that under certain conditions, even drug molecules that are very selective and specific for a certain type of receptor may spill over. They may spill over and interact with receptors that they're not supposed to, and that can be trouble, right? Okay. All right. So let's go back to our presentation here. Okay. And now we're going to get into a part of a really important part of the lecture here, okay? So if you right now are feeling a little tired, a little non-focused, okay, or you've been distracted, okay, I'm going to ask you right now to get your game face on and get focused, okay? Stay with me for the next 10 minutes, all right? Because if there's a hard part to today, this is it. And it's really, I'm saying it's hard, but it's really not. But I think sometimes we tend to make it more complicated than it needs to be. So please, please, please stay with me. In the next 10 minutes or so, we're going to be talking about selectivity and specificity. Now, these are two terms that are very similar to one another. That's why it's easy to get them confused. And they are closely related to one another. So there's a lot of similarities between these two terms, but there are some important and distinct differences that you need to know. All right, so if we have a drug, you know, when we talk about drugs that we give our patients, we want them to be very selective and specific, okay? Drugs that tend to be very selective are also very specific, okay? If drugs are less selective and they're more promiscuous, they tend to be less specific, okay? So let's start talking about some definitions here, okay? I want to move ahead 2 slides. I'd like everybody to move ahead 2 slides to selectivity. I want to start with that one first because I think that makes the most sense, okay? So selectivity, as the definition I have up there, is a term or a word that is used to describe the ability of a drug to select or distinguish, okay, between similar receptor types, okay, or for its preference for one receptor over another, okay? So one of the analogies that I gave you guys, okay, was that pretend you're a drug molecule and you enter into a large crowded room and you're looking for your significant other in that large crowded room, okay? And you're able to scan the room and you see your significant other there, okay? And you're able to go over and interact with them, okay? That means that you are able to select or distinguish your significant other from everybody else in the room, okay? All right. And there's a reason why you want to interact with your significant other and not some random stranger there, right? Because you have affinity for your significant other. Okay. Let me get an example, another example of this. This is Dr. Culhane's lunch bag here. Okay. So if I'm looking at my lunch bag here, I'm seeing what I've got for lunch. Okay. I've got 2 snacks for today. Okay. I've got a bag of peanuts and raisins, and I've got a bag of celery, okay? So pretend I'm a ligand, and these are 2 receptors, okay? I can tell the difference between this celery and this bag of peanuts and raisins because they have different physical characteristics, different colors and shapes, right? So I can select between these 2. And if I were to select one of these as my favorite snack, okay, it's not going to be the celery, right? It's going to be the peanuts and raisins. All right, so I've got 2 different receptors here. I can tell the difference between the 2. And I have a preference for this one over this one. Does that make sense? Now, let's say that I haven't eaten all day and I'm starving, okay? And I look at my lunch bag and I've got this little bag of peanuts and raisins and I got this bag of celery, okay? Guess what's gonna happen? Am I gonna just select for one of these? No, I'm gonna eat both of them. Even though I have a preference for the raisins and peanuts, I'm going to eat the celery too because I'm really hungry. Drugs that are at very high doses will bind to both of these receptors. Just like when I'm super hungry, I'm not going to be particular. I'm going to eat both of these. See the analogy there? Now, if it's right after lunch, let's say it's 1 o'clock and I've had lunch an hour ago, and I'm a little bit hungry and I'm like, hey, I could use a little bit of a snack. And I got this choice here. I got celery or I got peanuts and raisins. What am I going to select for? Probably the peanuts and raisins, right? That would be analogous to a drug at very low doses. Does that make sense to everybody? But as we bump up the dose of a drug, or as I get hungrier and hungrier, I lose selectivity. I'm going to eat both of these because I'm hungry. Make sense? All right, good. I'm going to put this one away and I'm going to keep the peanuts and raisins out for a second, okay? And we're going to, because I'm starting to get hungry and we need it for our next example. Any questions about that so far? All right.
In both cases, though, we're still discussing selectivity.
Yes,
right?
exactly. This is all about selectivity, the ability to distinguish between one receptor and another, okay? Or one type of receptor and another type of receptor, okay? And usually, I'll tell you the truth, folks, when I do this, I usually bring in props to the classroom, like I'll use Skittles and M&Ms and, and Reese's Pieces. But unfortunately, we can't do that this year. So I'm just using what's in my lunch, okay? So selectivity is the ability to distinguish between one receptor type and another, okay? And again, it also tells you a little bit about the preference that you have, okay? Now, let's take a look at my actual example here, okay? Drug A is given to a particular biological system. Maybe you're giving it to a patient at a dose of 4 milligrams, okay? Now, the system contains 4 different types of receptors, okay? Actually, 3 different types of receptors, X, Y, and Z. There's a typo there, okay? At 4 milligrams, drug A is selective for receptor X over receptors Y and Z, okay? So at a relatively low dose of this drug, drug A, which is designed to interact with receptor X, is selective for receptor X over Y and Z. It can tell the difference, okay? And it will bind to receptor X because that's its preference. This is just an example, okay? Let me give you a specific example of this now, a real life example, okay? Bronchial smooth muscle expresses 4 types of adrenergic receptors, okay? So the smooth muscle in your lungs expresses or produces 4 types of adrenergic receptors, alpha-1, alpha-2, beta-1, and beta-2, okay? If we were to give the patient 10 milligrams of epinephrine at that dose, okay, epinephrine will bind and activate only beta-1 and beta-2 receptors. It will not bind to and activate alpha-1 and alpha-2 receptors. So in this circumstance, we can say that epinephrine is selective for beta receptors over alpha receptors. Just like when I'm not really hungry, okay, I'm selective for the relatively unhealthy snack, I wish this was a bag of Skittles, versus the really healthy snack, okay? Does that make sense? Now, let's take a look at the example 2 here, okay? Let's say that we rewrite this example, and now the dose of epinephrine that we're giving our patient is 100 milligrams. Can you make a prediction about what might happen in this situation with regards to receptor binding and activation?
It's going to bind all the receptors.
Absolutely, Roberto. The probability is that we're going to get activation of all the receptors, right? So selectivity, and you should write this down, okay? Selectivity is dose dependent or dependent on the dose of drug that we're giving. So selectivity is dependent on the dose of drug that we're giving. Drugs tend to be more selective at lower doses. and drugs are less selective or they lose selectivity as you give more and more of the drug?
It's going to depend the of the person that is taking the medication.
Roberto, there will be biological variability, right, between, and patients' responsiveness to drugs. Absolutely. But you know what, I think we're just gonna imagine that that's not the case here, and we're just gonna take a look at what's happening at that molecular level, right? Okay, a good point. Definitely, different patients will process and interact with drug molecules in different ways, right? Okay. All right. Any questions about this? Everybody understands selectivity. Victor, you got a question?
Yeah, the only assumption I'm making is that the reason why when you give someone more medication, they're more prone to side effects, because more stuff is being like different receptors are being targeted instead of the ones that you want.
Exactly. That's one of the major reasons. It's not the only reason, but it's one of the major reasons why you see drug side effects in patients. Okay. There are lots of other different reasons, but for the purposes of our discussion here, this is a pretty significant one. Okay. And that's why, when you have a patient that needs to be started on a beta blocker for some reason, right? Okay. We don't just, as pharmacists, we don't just recommend the highest dose of the beta blocker be started, right, in that patient. Why don't we just give them the most beta blocker that we can give them right off the bat, right? Okay. First of all, we don't know how they're going to respond to it. And this gets back to Roberto's thing that, patients will respond differently to different drugs. But we also run the risk of developing side effects. So anytime a drug is prescribed, we're trying to give it at its lowest dose possible to get the therapeutic effect that we want, and also to try to avoid side effects. And sometimes we have to bump that dose up higher and higher in order to get the therapeutic response that we're looking for. The trade-off there is that the probability that side effects are going to occur increases. Okay, so there's always that trade-off, risk-benefit analysis. Okay, everybody got that? All right. Now let's go back. So here's just this next slide really quick here. This just reiterates what I've already said. Selectivity is a dose-dependent phenomenon, okay? As the dose of drug you expose your biological system to gets higher, okay, the ability of a drug to distinguish between two separate receptors decreases. So your drug molecule or your ligand gets more promiscuous. It starts to interact with receptors that it's not supposed to at higher and higher doses, okay? And here's the examples that I was using here, okay? And you can notice we've gone from 4 milligrams to 40, 10 milligrams to 100, right? And what's happened in each of these cases is that drug A and epinephrine are now interacting with all the receptors possible that it can. Okay? This is just a reiteration of what I said before, a repeat. All right, let's go back a couple of slides and talk about specificity. Okay? So, specificity is a term that is used to describe what receptor or group of receptors a drug will actually bind to. Selectivity is the ability of a drug molecule or ligand to distinguish between one receptor type and another, and it establishes its preference. Okay, again, I got two receptors here. Okay, I've got the celery receptor and I got the peanuts and raisins family of receptors here. All right, I am selective for the peanut raisin receptor family over the celery family here, okay, of receptors. Now, specificity actually determines what specific type of receptor or group of receptors a drug will interact with. So, for example, we know that I am selective, okay, for the peanuts and raisins over the celery, right? But what about the individual little receptors in this bag here. I got peanut receptors and I've got raisin receptors. Which one? We know that I prefer the peanuts and raisins, but under what, under a particular circumstance, am I going to eat just the raisins? Am I going to eat just the peanuts? Or am I going to eat both? That's specificity. All right. So let's say I'm selective for the peanuts and raisins receptors over the celery receptors. That's my selectivity. But when push comes to shove, okay, what I'm really specific for are the raisins. Delicious. Okay. So that's specificity. All right. If I'm not really hungry, if I'm at a low dose and I have my choice, I'm going to interact with the raisin receptor, not the peanut receptor. Okay. Let me give you another analogy here. Okay. Again, you're coming into let's say you're at a family reunion. Okay. Events that everybody loves to have, and hopefully someday we're going to be able to have again, right? You're at a large family reunion. You have a big family, right? You've got 100 people there, okay? And let's say you've got a group of family from one part of the country that you're from, okay? And you've got another big group of family members from another part of the country that you're from, okay? And let's say you're from this part of the country and not from this part of the country. So you're more selective for people that you're familiar with. These cousins over here and, and relatives, aunts and uncles and cousins over here. So you walk into the room, you're scanning the room, all right? You're seeing two distinct groups of people. You got your aunts and uncles and cousins from the part of the country that you're from, and then you've got this other group of family members from a part of the country that you're not from, okay? Which one are you going to be selective for? Which one do you think?
The one where you're from.
Yeah, exactly. So you're probably going to be selective for the relatives that you're familiar with, that are from the same part of the country with, that you know really well, maybe not over here. Now, once you go over to this group of relatives, right? Let's say there are 10 people in that group, okay? Now you've got to pick a person to interact with or persons to interact with, okay? This is specificity. Okay, determining what group you want to interact with and you have a preference for selectivity. And then once you get to that group, now you're going to look at which people in this group do I want to talk to. That's specificity. All right. So you know that your Aunt Marge, your Uncle Joe, and your cousin Sam are obnoxious. All right. And you don't like them and you don't want to talk to them. Okay. Are you specific for those receptors? No. But you love your Aunt Sally and your cousin Sarah. So you're going to talk to them. Are you specific for those receptors? Exactly. Okay. So in this group of family members here, you are specific for Aunt Sally and your cousin Sarah. Okay. You're selective for this group of family members because they're from the same part of the country that you're at. But when you go and you start interacting with them, there are two that you're specific for, Aunt Sally and Sarah, because you love them. You don't like your other aunt, uncle, and cousin who are obnoxious, right? So you want to try to avoid them. Does that make sense? Okay. Let me give you some actual real life practical examples here on the slide. Okay. All right. So the other thing I like to say about specificity is that when we talk about specificity and you're doing a specific example, it's important to actually list out the specific receptors that a ligand will interact with. Okay. For example, okay. Here, I'll give you the example here. Drug A is specific for receptor X at a dose of 4 milligrams. So we're naming the actual receptor that we're talking about here, okay? Epinephrine is specific for beta-1 and beta-2 receptors at a dose of 10 milligrams, Okay, so let's take the epinephrine example here, right? Okay, epinephrine can interact with adrenergic receptors, right? And there are two families of adrenergic receptors. We have alpha receptors and we have beta receptors. At 10 milligrams, what adrenergic family of receptors is epinephrine selective for? Alpha or beta? We saw that in the last example.
Beta.
Beta, right?
Mhm.
Now, if we're going to talk about specificity, we have to get a little bit more detailed and list the specific beta receptors that epinephrine will interact with. Beta 1 and beta 2. Okay? So with epinephrine, we can say that at a dose of 10 milligrams, epinephrine is selective for beta receptors over alpha receptors, right? It can tell the difference and it has a preference for beta receptors. And then if we were to say something about the specificity, we have to get more specific and detailed. We'll say that of the beta receptors that epinephrine can interact with, it is specific for beta 1 and beta 2. Okay? And you'll see these terms used all the time in the pharmacy literature when we're talking about drugs, selectivity and specificity. Okay? Now, selectivity or specificity, just like selectivity, is a dose-dependent phenomenon. Okay? We lose specificity as the dose of the drug increases. Okay? So as you increase the dose of a drug, remember, in any biological system, the probability or possibility that that drug or ligand will interact with another type of receptor increases, right? We know that. We've talked about that. So it should make sense that the more drug we give a patient, we start to lose selectivity and specificity. Let's take a look at epinephrine here. Again, down here. All right. We know that epinephrine is selective for beta over alpha receptors at 10 milligrams, right? And we know that at 10 milligrams, it's specific for beta 1 and beta 2 receptors. What happens when we bump the dose up to 100 milligrams? What happens to the selectivity now? At 100 milligrams, is epinephrine able to distinguish between alpha and beta receptors essentially? Nope. We've lost selectivity. It's non-selective for our adrenergic receptors, we say. That's the term that we use at 100 milligrams. What's its specificity at 100 milligrams?
Alpha 1, alpha 2, beta 1, and beta 2.
Absolutely. So we were to say at 100 milligrams, epinephrine is specific for alpha 1, alpha 2, beta 1, and beta 2. So when we bump the dose of a drug up, we tend to lose selectivity and we lose specificity. All right. If you give a drug at a dose of at any particular dose, and there's a huge long list of receptors that drug will interact with, is it very specific?
No.
If you give a drug at a certain dose and there are only 2 types of receptors that it might interact with, is that drug more specific? Absolutely.
Yeah.
Okay. You see what we're saying here? All right. So again, selectivity, tells you a little bit about the, kind of the preference that a drug has or a ligand has for a group of related receptors. All right. One family from one part of the country over another family. One snack type, unhealthy versus healthy. Okay. And then specificity will tell you something about the specific individual receptors that drug will interact with at a given dose. Okay. Alpha and beta are 2 groups of receptors. Okay. If a drug is selective for beta receptors, maybe it only interacts with beta 1 and beta 2, but not beta 3 and beta 4. So it's specific for beta 1 and beta 2. Okay. Make sense? All right. I'm going to pause here for a second. And I am going to ask questions. Ask for questions because we're getting close to the end of class and I'm not going to get into anything new. What questions do you have?
I have a question.
Sure.
So when you're manufacturing like a new drug, do they sort of use those constraints in that order? Like first they'll make sure the drug is selective for certain receptors, and then they make sure the drug is specific for certain receptors?
Right. That's in theory, that's the way that it works. It doesn't always work that way, but that's if I could do it that way, that's exactly the way that I would do it. Right. Let's say I want to develop a drug that slows down heart rate by blocking beta receptors. Right. So I might look at, okay, my drug compound that I'm looking to develop, does it interact with adrenergic receptors or muscarinic receptors? Right. We want to make sure, right, that it doesn't interact with muscarinic receptors. And then I'm going to go and say, okay, so we know it only interacts with adrenergic receptors. So which adrenergic receptor family will it interact with, alpha or beta? We want it to interact with beta, right? All right. And then once we've determined that it'll interact with beta receptors, then we can take a look at, okay, well, I know I've got 4 different types of beta receptors. And there's only one type that's really important in regulating heart rate in the heart, which is beta 1 receptors, right? So that's when we start to look at specificity. And, again, we have a lot less control over this in the drug manufacturing and design process than you might think. But, scientists will work with a pharmacophore and add different functional groups and remove different functional groups to improve selectivity and specificity, to improve half-life, right? So that we can, to increase half-life so that we can reduce the number of times a day a patient has to take the drug, right? They may work with the drug's chemical structure in order so that it can be formulated in a certain way, so that patients can take it orally versus intramuscularly, okay? So there's a lot of different things that are considered when drugs are being developed and brought to market. Selectivity and specificity is certainly one of them, but it by no means is the only one.
Okay.
Dr. Cohen.
Yes.
Okay, so you said intramuscularly. Would you still have that issue of specificity? But what I'm thinking is, wouldn't you be able to combat that if you just give a suggested amount over a longer period of time? Because if the patient's already in the hospital and connected to an IV, couldn't you just?
Yeah, sure, Victor. So, I mean, you can certainly, like I said, you can actually regulate the selectivity and specificity of a drug by regulating the amount of drug that a patient is getting at once, right? So if there's a difference, let's say we have drug A and we want to give the patient 50 milligrams of drug A. There's going to be a big difference in the selectivity of drug A and specificity of drug A if we give it all in one giant bolus all at once, right? So that the body is overwhelmed with the drug, versus if we infuse it in the patient over a 4-hour period, right? And the patient is getting a little bit of the drug every single minute, okay?
I guess my question is it easier intramuscularly to avoid specificity issues?
No, because really, again, we to some degree, we can, change the selectivity and specificity of drug by regulating the dose that the patient is giving. But ultimately, selectivity and specificity of a drug for a receptor is determined by its atomic composition and how well it fits with the receptor. Okay?
Okay.
Which, again, the only thing we can do with that is, during the drug design process, try to make it fit as, and again, this is very difficult because it's very, very difficult for us to really understand what a receptor binding pocket looks like, what kind of amino acids are present, what conformation or spatial conformation those amino acids are in at any given time to design a drug molecule that's going to be able to fit specifically into that receptor. A lot of it's trial and error, Victor. Okay. So for example, I can go to a locksmith and get a key that is cut to fit my office door lock specifically and selectively. It only opens that office door up. Okay, because I know, the locksmith can determine what the tumblers inside the lock, their orientation are, and how to cut the teeth in the key, right? But when we're dealing with drug receptor interactions, there's still so much that we don't know about receptors that our drugs target. Okay, that it's a lot of trial and error. Let's try this. Let's try this. Let's imagine taking a key blank to a locksmith, and they start randomly cutting teeth into the key. And okay, let's try this pattern. Does it fit in your door? Okay, great. We're off to the right start. Can you turn it? Nope. That means that the teeth aren't complementary to the tumbler. So we pull the key back out, and the locksmith cuts another pattern in it. And we keep cutting different patterns in the key until we find one that not only fits in the lock, but actually unlocks the door. That's really a great analogy, I think, for drug development. Okay. We take a pharmacophore and add and subtract functional groups until we finally get a drug molecule that will interact with a high degree of affinity with the receptor that we want it to. That's why developing drugs is so expensive, so time consuming, and so difficult. One of the reasons.
So the big hurdle of that is just understanding how the receptor is going to interact with the drug.
Exactly. And we've gotten a lot better at that over the last 20 years, but we're still not, not anywhere where we need to be, where we could, like, for example, plug a receptor, amino acid sequence of a receptor into a computer program, and it'll spit out, an exact molecule that will fit exactly with that receptor. Can't do it yet. Okay. Someday maybe, but not right now.
Okay, thank you.
You're welcome. Any other questions?
Yeah, I have a question.
Go ahead, Jodianne.
Using the epinephrine example there, we would have been saying that it's selective for alpha versus beta, but specific for beta receptors. If we're increasing the dose, why is it that it wouldn't have been that it loses its oh God, okay, I'm not gonna try. Anyways, for the beta, instead of like going back to alpha and beta, why wouldn't it be that it goes back to alpha in 1, 2, 3, 4 versus alpha and beta, if you understand what I'm asking?
Yeah, so I think, and let me see if I can answer that question if it doesn't seem that way. Okay, let me go back to the example here real quick. Okay, so with our example of epinephrine here, okay, and actually I have a table here. Let's take a look at this. This table may help a little bit with this question. I'm glad you asked it, Jodianne, because I forgot about it. And then I'll let you guys go. I know you know what? We're well past the time. Okay, you guys have another class? All right. If you need to go, please do go. And I will start here with this table on Friday. But Jodianne, in order to answer your question, I'm just going to use this table as an example. Okay. So if you take a look at this table here, and for those of you that need to go, please do. And I will start here and re-explain this again on Friday. So here's your epinephrine example, right? Okay, epinephrine at 10 milligrams and epinephrine at 100 milligrams. So you have two different doses of epinephrine. At 10 milligrams, let's start with a higher dose here first. At 100 milligrams, epinephrine will interact with all of the adrenergic receptors, alpha and beta, right? So it is non-selective. It's promiscuous. It's going to interact with all of the available receptors. If I were to ask you what the specificity for epinephrine is at 100 milligrams, what would you say? What would the list of receptors that you would give me that epinephrine interacts with at 100 milligrams?
Adrenergic receptors, beta 1, beta 2, alpha 1, and alpha 2.
That's it. That would be your specificity, right? Okay. Now, if we give a lower dose of the drug, like 10 milligrams, okay, now there's less drug in your biological system. And the probability that drug will interact with receptors that it's not supposed to decreases significantly. Okay. So at a much lower dose, what we see here is that epinephrine starts interacting now with the receptors that we want it to interact with, the beta receptors, right? So now and it does not interact with the alpha receptors. So at a low dose, okay, of epinephrine is selective for beta receptors over alpha receptors. And what's its specificity? Its specificity is it interacts with beta 1 and beta 2 receptors. That's the list of receptors that it will interact with at that dose. Okay? So what we can see here is that the types of receptors that epinephrine interacts with changes as we change the dose, right? At a very low dose, it interacts with only a couple of receptors. At a higher dose, it interacts with lots of different receptors, okay? And so we can use our terms selectivity and specificity to describe, okay, the interactions that epinephrine has with these receptors at different doses. At 10 milligrams, we can say that epinephrine is selective for beta receptors over alpha receptors. Okay. We could also say that epinephrine at 10 milligrams is selective for beta receptors over muscarinic receptors. Or it's selective for beta receptors over serotonergic receptors, right? Okay. It's just, this is the group of receptors that it prefers to interact with. And then if we want to say something about the specificity of epinephrine at 10 milligrams, we say that epinephrine is specific for beta 1 and beta 2. We name the receptors that it will interact with when we talk about specificity. Okay. When we bump the dose up to 100 milligrams, now epinephrine is interacting with both adrenergic receptor families, not just the one from your part of the country that you're from, but also the ones that you're not, from the part of the country that you're not from. So if you're at that family reunion for 5 or 6 hours and you've had a couple of alcoholic beverages or adult beverages and you're interacting with people, you might be shy at the beginning of the night and only interact with the group of family members that you know. But even then, there's only a couple in that group that you really want to talk to. But by the end of the night, as you get to know people and you're more relaxed, right? Now you're going to start interacting with everybody. And that's analogous to increasing the dose of a drug. Okay. Now epinephrine is interacting with both family of receptors, the alpha receptor family and the beta receptor family. And it's specific for, it will talk to all of them, beta 1, beta 2, alpha 1, and alpha 2. Okay, does that make sense? Jody Ann, does that help?
Yes, it does. So it also loses the selectivity as well, right?
Exactly. You lose both selectivity and you lose specificity as you increase the dose. And don't be confused by the fact that as you lose specificity, the number of receptors that your drug interacts with will increase. That's an indicator that you're losing specificity. Okay?
Dr. Gohane, see,
yeah.
I understand the concept, but I just don't understand. Can you use them interchangeably? Because they both are affected by the same thing. And they also...
You know what, Justin, they both change the same way. Okay, so yeah, as you lose selectivity, you're going to lose specificity. As you gain selectivity, you're going to gain specificity. Drugs that are very selective are usually pretty specific. Okay, the thing is that they mean slightly different things. Okay,
yes, because one is...
Yeah, with selectivity, you're comparing the preference that a drug molecule has for a group of related receptors to another group of related receptors.
Like adrenergic and muscarinic,
or two different types of adrenergic receptors, alpha versus beta. Okay.
And would specific mean like beta 1, like metoprolol? That's a beta 1 blocker. Is that the specificity?
Yeah, so exactly. So if you were to use metoprolol, right, which is the beta 1 blocker, right? Okay. What can you say about its selectivity when we compare it to when we look at its ability to interact with beta and alpha receptors?
Well, it's selective for beta receptors
over
alpha receptors.
Right. There's always that comparison over, you know, it's preference for one over another, right? Now, what can we say about its specificity?
That would be that it's a beta 1 specific, right?
Yeah. So it's specific for beta 1 receptors.
Okay.
Got it?
I got it.
Now, that doesn't mean that metoprolol won't block beta 2 receptors if you bump up the dose and you give a high dose of it, right?
Yes. Will it also, if you bump up the dose, will it also block alpha receptors?
You know, theoretically, if you give it at a high enough dose, okay, it could. You might kill your patient at that high of a dose. You might stop their heart, but that's possible.
Okay.
Okay, but typically within the therapeutic range, like with metoprolol, we have a specific therapeutic range that we give it. And in that range, right, at the lower doses, metoprolol, at the low end of that dose range, metoprolol is very selective and specific for beta-1 receptors. Okay. As we bump it up, it starts to lose specificity and can potentially block beta-2 receptors as well.
Okay.
Does that make sense?
Yeah, that makes sense. Should we download this
still
screenshot? I'm
selective.
scared,
Even
Victor.
at those higher doses, it's still selective for beta over alpha. Okay. But
Yes.
we're starting to lose specificity.
Okay.
Okay.
Dr. Coyne,
Yeah, Victor.
I had a question about the mesoform thing or meso.
Yeah. Oh, you know what? I forgot to go over that. We'll go over that on Friday. Okay. But
Okay.
yeah, if you have a question about it, go ahead.
Okay. Can you look at the chat? I sent the screenshot of the first question.
Yeah, hold on a second, Victor. Let me minimize. Let me first stop sharing because I'm trying to see all of you on the screen here. All right, so I'm going to stop share, and here we are. We're back, and then I'm going to go to the chat, and
I sent the second one with like the whole question and the first problem as well.
Yep. Let me see here. All right. Let me open it. Let me open it up here.
Okay. Open
file.
A couple of us that in the class were having trouble trying to get a defined answer for it.
Yeah.
A lot of it was kind of guesswork, so we were just trying to see.
Yeah. Is it about the Henderson-Hasselbalch?
The first question, which is whether or not the compound has physicochemical properties required to act as a drug molecule.
Exactly. Okay, go ahead. So what do you think, Victor? So we talked about those physiochemical properties, right? Size, shape, molecular weight, right? What do you think? Do you think that this drug has the appropriate molecular weight to be a drug molecule?
The one thing that we ended up getting stuck on was, I think we need to know whether it's an acid or base in order to proceed.
Right. So that's question number 3, I think, in terms of it gives you the pKa value. Okay. And whether it's absorbed, where in the GI tract might it be absorbed based upon the pKa value? Okay. We'll discuss that on Friday. But I do want to say is that this drug molecule indeed does have the characteristics. This molecule does indeed have the characteristics needed to be considered to be a drug molecule. It's got a molecular weight of over 100 milligrams or grams per mole, right? Does it have unique functional groups that might lead to the formation of ionic van der Waals or hydrogen bonds?
Yeah.
Absolutely. Okay. And does it have a kind of a unique shape to it? Yeah. Okay. So I'd say that, yeah, based upon those very, very basic characteristics, just that, yeah, is there a potential for this drug molecule to be this molecule to be a drug molecule? Yes, absolutely.
So then what would write it off as not being a drug molecule? Like what would be something you could physically see and be like, this is not a drug molecule?
If I gave you a molecule like an ethyl molecule, right? Okay. Something very small.
Okay.
Or maybe a hydrocarbon chain with 5 carbons on it and just hydrogens. Okay. Is that really big enough and complex enough and have functional groups that would allow it to selectively and specifically bind to a receptor?
No.
No, probably not. So is that have a good possibility of being a drug molecule? No.
No.
No, because there's nothing unique about it. It's too small. There's not really a lot of uniqueness to it in terms of its size and shape and molecular atomic composition, right?
Okay.
All right. So it's those sorts of characteristics that, again, make a molecule interesting as a drug target. And this is a very interesting molecule. It's got a number of aromatic rings. What kind of bonds might those aromatic rings form with the receptor?
Van der Waals,
Yeah, van der Waals, right? How about that carboxyl group?
That's ionic.
Could be ionic, right? And how about those hydroxyl groups?
Hydrogen.
Yeah, exactly. So there's some unique functionality to this molecule that would suggest that it could potentially form multiple types of bonds with a potential receptor target. Okay.
Okay.
Does that make sense, Victor?
Okay, so the ability for the molecule to attach in different parts of it gives it like a drug.
Yeah, because it suggests that this drug molecule can form unique chemical interactions with a specific type of protein, right? Versus a let's say a 4 or 5 carbon hydrochain or a hydrocarbon chain, right? With no functional groups on it, right?
Oh, I see what you're saying. Okay, that makes sense. So a big giveaway is this functional groups and the different types of bonds it is able to make.
Exactly. That's it, right? Because that's what we want, right? That's what selectivity and specificity is all about. The drugs that have unique chemical structures, right? And have functional groups that are positioned right spatially that might be able to interact with a receptor, okay? Make it a decent candidate for potentially being a drug target. Now, does this mean that this is going to interact with anything? No. Okay. But it has the potential to, right? It does have the potential to form all those different types of bonds that we talked about, all right, with our receptors. And so it's interesting enough to continue to explore.
Okay. Okay, that makes sense.
Right? Now, if you're going down to question 2 or 3, I think with the pKa value, okay, if you want to you don't have to get into Henderson-Hasselbalch with that. If you want to, you can consider this drug to be a weak acid.
Okay.
Okay? But you don't have to do a Henderson-Hasselbalch. Okay? If you look at the pKa value, and again, I'm trying to remember, I think the pKa value in this case is 4.8, right?
Yeah.
This drug. And typically we assign pKa values to a specific functional group on the drug molecule, like maybe this carboxyl group, for example, has a pKa value of 4.8. I just gave you a generic pKa value for the entire drug molecule, okay? So pKa, all right, is typically is representative of the pH in which a functional group or molecule has a neutral charge, right? Or I'm sorry, where 50% of the drug molecule is ionized and 50% is unionized, right? So you got 50-50. In this case, if you put this drug, if it's a weak acid, if you put it into a more acidic environment, a greater portion of the drug molecule will be unionized, right? Okay. And more readily cross biological membranes via passive diffusion, okay? If this drug is put into a basic environment with a pH greater than 4.8, a greater percentage of the drug molecule will be ionized and will most likely not cross biological membranes relatively well. Okay. So in this particular case, this drug is more will be absorbed more in acidic parts of the GI tract than those that are more basic.
So at that point, do we look up on Google like the different pHs of the GI tract?
You can if you want to get crazy like that, absolutely, right? Okay, you could definitely do that. You could do Henderson-Hasselbalch here to generate some numbers that will reflect what I'm telling you, okay? But I think really what I wanted to do in this particular case is, I'm glad you're reaching for Henderson-Hasselbalch because that's where you need to go with this, but I wanted to keep it a little bit more simple than that and just say, look, if you understand what the pKa value is, right? And you can kind of make a prediction about, now normally, yeah, Henderson-Hasselbalch equations would be run, degree of ionization would be determined so that we can get a real specific understanding of where this drug is being absorbed at, if this is actual drug development. But because we're just playing around here, all right, we're just going to kind of eyeball it.
Okay.
Make sense?
Yep. Thank you. That was a great explanation.
All right, good. Everybody good?
Yeah, Dr. Cohen, I have a question about the attendance. I just want to know if you mark me present.
Yeah, so so in terms of attendance, okay. So basically what will happen in pharmacotherapeutics with your instructors is, again, if you're there at the time class starts, you're marked as present, okay. If you are late, you'll be marked as late and it'll count towards, one of your excused absences, okay? Or if you don't show up, it'll be counted as part of your excused absence, okay? I will tell you guys, different instructors some are very, very militant about this, right? And want you there at the time, otherwise you're absent and whatever. I'm trying to get you prepared for that. Okay. Other instructors may be a little bit more lenient. The best rule of thumb is to be there on time to make sure that you're there. Now, what I always tell students is, okay, and that's why I keep attendance like this. If you're late, okay, and let's say, you know, it gets to the end of the semester, and let's say you had 2 absences because you were, let's say you had 4 absences because you were sick with COVID, God forbid, but let's just imagine that that happens, okay? And you have that 1 late, okay? And because of that 1 late and those 4 absences, you're getting 3 percentage points taken off of your final grade, okay? And if you only had 2 percentage points off, it would mean that you would pass versus having the 3 taken off. I won't count the late as being absent. Okay, does that make sense?
Yeah, but am I late because it was like 4 minutes?
Yeah. So Laura, what I do, you know, and you know what faculty will do is they will have their, you know, when we're in class, they'll have their clicker, their attendance slide up. They'll take it down, write it, you know, the time the class starts. So if class starts at 8:30, for example, it comes down. And if you know, if you're not there at that point, you know, what I would do is recommend I'd go up to the instructor and let them know, hey, I'm here. I know I'm late. I just wanted to let you know that I am here. They appreciate, or email them later on and say, hey, I'm here, so that they can make a note of it. Okay. All right.
It was because today I was 4 minutes late. That's what I'm asking you.
Yeah. So if you're 5 minutes late, you're late. If you're 2 minutes late, if you're 30 seconds late, you're late. Okay.
Yeah.
All right. That's just the way the policy is. And like I said, that's why we give you some freebies. So hopefully, you know, it's not an issue. Okay. And, you know, if, like I said, if it comes down to the point where that late might cause you to not pass the course versus pass the course, typically most instructors won't take that into we'll take that into consideration and won't count that off of your final grade. Okay.
Now, will you always take it manually, or
what's that, Laura?
Will you take it manually? Or
Yeah, we always do. And, you know, I mean, it just depends on different instructors. Some instructors will use Exam Now for attendance, but the same thing is, you know, with the waiting rooms, right? Okay. They will, you know, at 8:30 or whenever the class starts, you know, they'll keep people in the waiting room until they take attendance, especially if they're taking it by hand. And then before they start teaching, they let everybody in. Okay. So make sure you're on time. Make sure you're early.
Okay.
Okay. Now, if you're having internet connection issues or something like that, you know, you can't get on, all you need to do is email me and let me know. Okay.
Yeah.
All right. Any other questions, folks?
One more question. So this Friday is recitation?
Yeah, we're going to review certainly the memoranda 1. Okay. And but I will probably be teaching.
Okay. So since we're about almost like 2 weeks out to the first exam, just as study practice for what we may see, is it a good idea just to keep going over like the study stop questions and
stop and self-assessment questions, right? Okay. So the self-assessment questions are practice questions for any type of application question you're going to have on the exam. If you can do those self-assessment questions, the probability that you can get the application types of questions right on the exam are really good.
Okay.
That's why I'm giving you, and even on the memoranda, I'm giving you tons of practice, okay, for stuff that you're going to see. Using the study stop questions is a great way to practice active recall on the material. I also recommend the boxing and unboxing technique for this, okay, so that you can gauge, you know, what your learning is as you go along. All right. All right, and I need to let you guys know about office hours too. I will get on that today and make sure I send out an email about that. Okay.
I know I asked Dr. Skabinski, but I just wanted to make sure it's the same with you. Your recordings, Sean is still uploading them and he'll process them.
I'll try to get those done today or tomorrow too for the first couple of ones that I have. Okay.
Thank you.
All right, guys. Have a good one.
Dr. Cohen.
Yeah.
So any of the questions that we have about for the study stop, will we be able to go over those on Friday?
We can, absolutely. If you want to, we certainly can.
I know
Okay.
you explained one concept, but after speaking with my study group and going back, we still have some more questions on that. So
Yeah.
maybe the same question. Okay.
Absolutely. So what I'll do is I'll take the first half an hour of class on Friday. I'll go through the memoranda. I'll take any questions about study stop questions or self-assessment questions, and then we'll move back into the material.
All right. Thank you.
All right. Sounds good. Thanks, folks.
Thank you. Have a good one.
All right. Bye-bye.
Later.
Take care, folks.